video is about CAN and CANopen security. So how do we protect our CAN and CANopen systems using methods available today?
We would like to thank you, our partners at NXP and the Hochschule Offenburg, for their contributions. Our combined findings will be presented in papers at the Embedded World and the International CAN Conference. Before getting into the details, let's review the motivations of hackers. So what are possibly the motivations that someone would want to hack our CAN or CANopen system? Not sure if that's really a motivation, vandalism, but there definitely are hackers that simply try to break stuff or see how much damage they can cause. Then we have access to intellectual property, spying, reverse engineering, trying to rebuild your product. Extortion, like ransomware or disturbing your manufacturing process to extort money from you. There's hacktivism, meaning hacking due to politics, ethics, religion. Maybe someone just doesn't like you or stuff that you or your company is doing. Then there's jailbreaking. This could even be your customers, because maybe you have some safeguards and they can be disabled. And finally, we have terrorism, simply producing damage to the digital infrastructure. To have a real-world example, let's look at an elevator, a lift system. So we have a building with multiple floors. On each floor, a user interface. Somewhere there's the drive to bring the cabin or car up and down the shaft. We have a controller. Then the cabin itself with some buttons, door control, another motor to open and shut the door. And to have some isolation, you typically would use a bridge in between the cabin and the rest of the building. For diagnostics, there are options to connect locally, or maybe there's even a remote access interface somewhere to the internet so that someone from the internet side can do some diagnostic and maintenance to the system. We highly recommend that local diagnostic devices do not connect directly to the CAN buses, but through another device, like illustrated here, through the controller, because this gives the controller the ability to check if the local diagnostic device is authorized to get access, and only after authorization it passes on the CAN messages received through the CAN bus and vice versa. Let's review the different attack scenarios and start with the physical attack. Physical attack means direct hands-on access to the wiring to add or remove devices to get your hands on some of the components on the CAN network. And for our elevator example, a determined person will get access to the cabling or some of the electronic units. Physical attacks can include manipulation of sensors to bypass safeguards. Maybe here somebody manipulates the scale built in so that the potentially car could be overloaded. By cutting the wires, you would have a denial of service attack, so the system would stop from working. And these are the things we cannot protect on the CAN side. Also, if somebody has their hands on the electronic units, they can do in-depth analysis, try to use the debug port, or maybe send in individual chips for code or key extraction. And also here we have no protection on the CAN side, just the recommendation that you use a secure microcontroller unit where such sort of extractions are much more difficult. However, replacing or adding devices on CAN, this is something we want to start trying to protect you from, so that injection, spoofing of frames, man-in-the-middle attacks, or even remote attacks become harmless or can be detected and secured against. Remote attacks are far more attractive to many hackers because it potentially gives them access to many systems and not just an individual system like with a physical attack. So every internet connection or potentially usable connection towards the internet needs to be examined and protected. Every internet connection we have in our CAN system requires protection because hackers are continuously scanning the internet for vulnerable systems. The challenge today is that with devices and networks and systems getting more complex, do you truly know if there's only one internet connection in your system? Maybe there are some more complex devices in your system that have a Bluetooth or Wi-Fi interface, or maybe are a gateway to a different network technology. So these are all potential entry gates for hackers and require protection. And for completeness, let's also look at the backend attack. So from a system that sits somewhere in the back and has remote access to our CAN system. A backend system that has authorized access to our CANopen system for remote diagnostic maintenance or data collection, well, it has all keys, all credentials. So if that is compromised, there's nothing really we can do on the CAN level to protect from this sort of scenario. We just mention it here for completeness. We will now summarize the protection methods available for your CAN system today. There are three methods that can be used to secure CAN communication. Number one, the CAN ID guarding. This works on the data link layer on the lowest level and protects your CAN messages without cryptography. We'll look at the details a little bit later. Then there is the CAN cryptographic layer. This is where our own CANcrypt comes in, which is a framework to protect individual messages. And last, we have the public-private key encryption and authentication that can be used with DTLS, where a few hundred bytes need to be exchanged to properly secure and protect an individual communication. CAN ID guarding is implemented in secure transceivers. These transceivers ensure that a CAN frame that does not belong on the network is destroyed by error frames. Now, how does a transceiver know if a CAN frame is allowed to be on the bus or not? Well, it simply protects the CAN IDs used by the CAN device it's connected to. So if the CAN device it's connected to is allowed to transmit ID number 5, and it sees that ID number 5 is used by someone else on the network, then it actively destroys that number 5 out there on the network. So this prohibits injections into the network. A second option is that it also limits the CAN ID the locally connected device can use. So if my local device that I as a transceiver am connected to is compromised and suddenly tries to transmit messages that do not belong to it, or it shouldn't be transmitting, well, these also do not go through. And then there's also a time filter, though, so that messages cannot be transmitted in a flooding manner by the local device. In our example with the elevator, ID guarding would be applied always to a local domain. So we would have one domain being the cabin, the car network, and implement ID guarding in all the transceivers there. And the second system would be in the building. Here, the floor, drive, and controller, they would also all use ID guarding to protect that local domain. The CAN cryptographic layer uses a shared symmetric key that is dynamically updated, so cyclically updated and refreshed to provide a cryptographic checksums for messages. The security method involved here is typically a lightweight block cipher, and we can now use authentication and optional encryption on a CAN message base. The nice thing on this level is that it works across domains. So even if there's a bridge involved and we have multiple CAN networks, then still multiple participants can form a secure group and have a shared secure heartbeat. And last, we have DTLS, Datagram Transport Layer Security. This is internet-grade security that we can also apply to CAN. However, it always requires multiple messages to be transmitted. It's not suitable to secure individual messages. Therefore, it's typically used for point-to-point security, endpoint-to-endpoint security when we leave the CAN domain. So for remote access or to identify and authorize local communications that are temporary, like a diagnostic device or a tool connected that needs to identify itself. These sort of connections is what we can protect using DTLS. Reviewing the CAN communication layers, we have the physical layer and the data link layer at the bottom. Those are provided by the CAN controller and are typically in hardware. On top of this, we have the protocol message layer. So this is where the higher layer protocol defines single CAN messages that are communicated. Another layer up is what I call the protocol service layer. Here are message sequences, because here the protocol implements certain sequences, responses, requests, segmentation, multiple messages, that sort of stuff. And then finally at the top we have the device and application profile layer where application data is communicated. Now, how do the three methods we introduced earlier fit in here? Well, the ID guarding sits right here on top of the data link layer. The CAN crypto layer is just at the bottom of the protocol message layer, because before it passes on the messages up, it verifies if the cryptographic checksums match. And the DTLS layer is here at the top. When doing the application data exchange, it protects specifically that application data. This concludes this video, so thank you very much for watching. Here's a brief outlook to other videos we've already published or which are in preparation. So next would be the three methods, in-depth description on how they work. So one on DTLS, one on the CAN cryptographic layer, and one on the CAN ID guarding. We want to publish a video after that for combining these security methods. So how can you properly combine these methods that they complement each other, so that you avoid duplicating work where it's not required. And the last video planned is the development and deployment of such systems. So here we have the considerations also for things like key deployment to these systems.